Welcome. This module explains the use of four engineering economy factors that involve uniform series A, a present worth amount P, and a future worth amount F. The detailed derivation of each factor is available in your textbook, and the factor values are found at the rear of the text. The first factor finds the present worth P of a series of uniform amounts, each amount being A, that occurs continually from time period 1 through time period n. In the cash flow diagram at the top of the slide, notice that P is located one time period prior to the first A value. We derive the factor to find P later. The second factor discussed below is the reverse, in that A is the unknown and P is estimated or known. Now, the first uniform amount A takes place one period after P, which occurs at the time t equals 0. A continues for n periods. The standard notation to find P or to find A is shown to the left of each diagram. Remember, the order of the letters in the factor is important. The first letter is always what is unknown, followed by what is known. Therefore, PA means find P given A. The third and fourth factors provide the same information, but for a future worth amount F. The series A is constructed in the same way, but the amount F is located in exactly the same period as the very last A value. For example, as shown in the lower diagram, F is known, or estimated, at period n, and the relation A is equal to F times AFIN, shown here, finds the equivalent uniform series A for periods 1 through n at a stated interest rate I. Now, let's get to some details to discover how these factors are derived and how to use them to answer questions. First, we'll consider the PA factor. This is the one used to calculate a P value in year 0, that is now, given a uniform series A that spans n time periods, as shown in this cash flow diagram. We will use years as the time period. As mentioned before, note that the factor will be derived such that P is located exactly 1 year prior to the occurrence of the first A value. To calculate P, we multiply each A value by the PF factor for the correct number of years between the location of A and the current time 0. The PF factor formula is 1 plus I to the minus t power, where t goes from 1 to n. The expression for P that you see here in the middle of the slide does exactly this. The series in brackets is a geometric progression. It needs to be simplified. This simplification is detailed in your text. The result is the relation at the bottom of the slide, shown here. The mathematical expression in brackets is the PA factor for n years, or n time periods in general, at an interest rate of I, and the relation P is equal to A times PAIN is the standard notation form. The interest rate cannot equal 0. Why? Because I is in the denominator of the PA factor. Now we have the first of our four factors. To summarize, this factor, the PA factor, calculates the equivalent present worth of a series of uniform amounts that occur over n time period at an interest rate of I% per year. This is what the cash flow diagram at the top of the slide demonstrates graphically. An example using the PA factor is presented later. This slide shows the reverse of that in the previous one. Now, we want to find the annual amount A that is equivalent to a present worth P. A will take place starting one period after T and continue for n periods. Again, let's use years as the time period. We solved the previous relation for A, and it does the trick. The relation shown here is the reciprocal of the previous factor. Now the AP factor is in brackets, and it calculates an equivalent A for n years given a known P and interest rate I. The standard notation for the relation is A is equal to P times APIN. Just as a reminder, note in the cash flow diagram that A starts 1 year after P takes place. Before an example, let's look at the spreadsheet functions that do the same as the PA and AP factors that we have learned. These are both single-cell functions. That is, no cash flows need to be entered into cells of a spreadsheet, only the function with the correct parameters between parentheses preceded by an equal sign. The present value, or PV function, displays the equivalent P amount for any combination of I, N, and A. Here, the series A must be known or estimated. I is entered as a percent, for example, 6%. If there happens to be a known future worth amount F also involved, it is entered last. If there is no F, it is simply omitted or entered as 0. Similarly, if the A series for N years is required for a known P, use the payment or PMT function. It finds the A value. Again, if there is a single F value known, it is entered. If none, omit the F or enter a 0. Both the PV and PMT functions display the opposite sign of the parameters entered. That is, if F equals plus 500 is entered for the PV function, the P value displayed will show a minus sign, or be displayed in red or in parentheses. This feature is built into the functions so that the result shows the sign convention of a cash flow diagram. This means that a payment, which is a cash outflow, of an amount A entered with a minus sign is calculated to be equivalent to a present worth amount P with a plus sign at time 0. To retain the sign input on the parameters, simply place a minus sign prior to the function identifier, that is, between the equal sign and the function name, PV or PMT. Here is a simple application of the PA factor. If Carla knows that she will receive $600 each year for 9 years, starting 1 year in the future, and if she is fortunate enough to make 16% per year on these 9 receipts, what is the present worth equivalent to her? Take a look at the cash flow diagram. P is the unknown equivalent, and A is the series that starts in year 1 and continues for 9 years. Notice A does not take place initially in time 0. It starts in year 1. The relation P is equal to 600 times the PA factor for 16% and 9 years is written, and the factor value of 4.6065 is found in the tabulated factor values, or using your calculator and the factor formula derived earlier. The answer is $2,764. This means that if Carla receives this amount right now and does earn 16% per year, it is economically exactly the same as receiving the $600 annually for 9 years and still making the same rate of return of 16% per year. If she were given the option to take either of the two, she should be economically indifferent to them. There may be other non-economic reasons to select one method over the other, but from an economic viewpoint, they are exactly the same at 16% per year. The AF factor does much the same as the AP factor, except that the future amount F is known, meaning it could be a target amount to accumulate at some time in the future. For example, if you wanted to know how much you must deposit each year for N years in the future to accumulate $10,000 at the end, you would use the AF factor to calculate A. One way to derive the AF factor is to take the formula for A that we have just derived using the AP factor and substitute the PF factor for P. Then simplify. The result is the factor in brackets at the bottom of this slide. It calculates the A needed to accumulate the amount F in year N. Note that the last A amount occurs at exactly the same time as F. As shown in this diagram, therefore, there is a last deposit of A at exactly the same time that the total amount of F is withdrawn. The relation at the bottom of the slide, A is equal to F times AFIN, is used to calculate A, given an I, N, and F value. As before, the reverse situation occurs when you know the uniform amount A and want to find the equivalent F value N years in the future. Solve the previous relation for F to obtain the formula for F is equal to A times FAIN. as is the convention, F occurs simultaneously with the last A value. As an illustration that uses the AF factor, we will determine the A series. Let's assume that a company has to pay a $6 million fine because it violated emission controls set by the government. As is often the case, the fine can be paid out in installments over a period of years. If money is worth 5.5% per year, and the company has 7 years to pay the equivalent of the $6 million, the cash flows are shown here. And the required annual uniform A series is found using the AF factor. The value for the AF factor at 5.5% interest and 7 years is 0.12096. Therefore, if the company sets aside $725,760 each year and makes 5.5% on each of these installments, the $6 million will be paid off in exactly 7 years. Think of the difference that 5.5% interest makes. These 7 amounts of $725,760 a year with no return will total only $5.08 million. The remaining approximate $1 million comes from the 5.5% interest on these installments. Now for the spreadsheet functions that provide the F and A equivalents. The future value, or FV function, requires an A series amount and can include a single present worth amount P. As before, P can be omitted or set equal to 0 if it is not involved. The same payment, or PMT function, that we used to find A earlier is also used to determine A when F is entered. If there is no P involved, enter 0 or place the 2 commas next to each other. Remember, the sign displayed on the answer is the opposite of that entered with the parameter A in the FV function or F in the PMT function. This slide shows the use of spreadsheet functions for all 4 of the uniform series factors that we have studied. After the following description, you may wish to pause the presentation to study the spreadsheets and their entries. For description purposes, let's concentrate on the right side of the screen, where uniform series A values are determined using PMT functions. The cells above the cash flow diagrams show what is given and what is to be determined. In the top frame, the present amount P is $6,000. Assume this is a loan to you, and the $6,000 you receive now must be repaid at 10% per year interest over a 10-year period. The PMT function is entered, and it displays the equivalent equal annual payment to be $976.47 each year. Note once again that the payments start 1 year after the principal of $6,000 is in your hands. Reflecting on these payments, you will repay a total of 10 times this $976.47, or $9,764.70 over the 10-year period, just for the privilege of borrowing $6,000 today. On the other hand, now look at the lower right frame. Here, the $6,000 is a future amount that you want to accumulate, so the equivalent annual series A should be less than above, because you have the power of interest on your side rather than paying the interest to the loan maker as above. Again, the PMT function is entered, and the result shows $376.47 a year. In this case, you need to deposit only a total of $3,764.70 over the 10-year period to accumulate the $6,000 in the future. Though this is a much smaller outgo than above, you will not have the use of the $376.47 each year, and of course, you do not get the $6,000 principal now because you borrowed no money. Pause the presentation now if you want to study these functions more carefully. This last slide will summarize the important guidelines about placement of the P, F, and A values when using any of these 4 factors, whether it is by formula, by tabulated factor value, or by spreadsheet function. First, P is always located one period before the first A value. Second, F is always located at the same time period as the last A value. Concerning the series A, it always starts one period after P occurs. And the A series will always stop at the same time as F occurs. If you remember these simple location rules, you will never incorrectly use the factors or the functions from the viewpoint of cash flow location. Well, that's it. You have completed this module on uniform series factors. Thanks so much for watching.